The James Webb Space Telescope is going to be the successor to the Hubble Space Telescope. An ambitious project, it aims to have a mirror with a combined surface area of 25 square meters, which is roughly 5 times bigger than Hubble's. Developments for it began in 1996, with an original launch date of 2007, but this date has continuously been pushed back. From the time of writing this script, the scheduled launch date is in March 2021. But what's the holdup? What is taking so long for this telescope to get into operation? Well, it's complicated. Literally. I'm Alex McColgan and you're watching Astrum, and together we will understand why the James Webb Space Telescope is taking so long. First of all, let's have a quick overview to this magnificent piece of engineering. The telescope features 18 hexagonal segments made of gold-plated beryllium. They combine to make a 6.5 meter mirror, the biggest that has ever been in space by a long shot. There is a very good reason for having such a big telescope in space, namely that in the vacuum of space, there is no atmosphere to get in the way of observations made by the telescope. If you have a look at videos taken by ground-based telescopes, you can see that there's a slight wobble to the image. This is due to the heat in the atmosphere, much like if you looked at a road on a hot day. That's not to mention all the dust and other particles in the atmosphere, reflecting and refracting light, which interferes with telescope observations. Technology is improving to counteract atmospheric influences on ground-based telescopes, but you just can't replace actually being in space. The other big reason for having the James Webb Space Telescope in space is that it is an extremely sensitive infrared telescope. And in this way, it is different from Hubble, which is only capable of looking in visible light and ultraviolet. In fact, the James Webb Space Telescope is more like the Spitzer telescope, another space telescope but with a much smaller mirror, only 85 centimeters across. Seeing as any warm object emits infrared radiation, a ground-based telescope would easily have its readings contaminated by nearby objects and the atmosphere. In the vacuum of space, however, the James Webb Space Telescope is protected from the sun by this massive sun shield, which means the scientific instruments stay a cool -220°C. Such a big infrared telescope will mean we can look back in time billions of years to just a few hundred million years after the Big Bang. This will give us an insight into the formation of the universe like never before. The James Webb Telescope will also look at individual stars, and even attempt to observe exoplanets, specifically to try and see the composition of their atmospheres. They do this by looking at the light spectrum of planets as its parent star shines through the planet's atmosphere. So, what's been the holdup over all these years? Well, the biggest delays were caused by the design specifications themselves. For instance, the mirrors. There is no launch craft that could fit a 6.5 meter wide mirror inside, so the mirrors had to be designed in a way that allowed them to be folded back during launch. This adds a massive amount of complexity to the design, as 18 hexagonal mirrors aimed at an object billions of light years away means that they must be aligned correctly to nanometer precision. As a result, not only do the mirrors fold out once launched, but each mirror can be controlled individually to a very fine degree. The other design challenge with the mirror would have been the weight of it. To use a mirror similar in weight to the one on Hubble would have meant that James Webb's mirror would be 10 times heavier than it is now, too heavy for a launch craft to get it to its final destination. So engineers used a groundbreaking design, a beryllium mirror that is light but also strong, and plated with gold for the reflective surface. Incredibly, with this design, each mirror segment only weighs 20 kilograms. You might wonder then, why don't they always use beryllium? Well, it is actually a very difficult metal to polish, and designers needed this mirror to be smooth to within nanometers. This adds a layer of difficulty to the building process. Beryllium also isn't ideal for reflecting infrared light, but gold is. You may look at these mirrors and think, oh wow, how much gold is on them? Well, actually, not much gold at all, less than 3 grams in total. How did they get such a fine layer of gold on these mirrors? Well, the technique they used is pretty ingenious. The mirror is inserted into a vacuum chamber, and some gold is vaporized into the chamber. The gold in this vapor form fills the chamber and condenses on all the surfaces, including the mirror itself. This gold condensation gives an extremely even finish, something that couldn't be accomplished through any other method. One of the other key design specifications of the James Webb Space Telescope was to be able to view hundreds of objects simultaneously. The way that they will achieve this is through some groundbreaking innovations invented specifically for James Webb. But this technology will go on to benefit many other sectors like biotechnology, medicine, and communication. Specifically, it is an array of microshutters that can measure the intensity and spectra of light from many distant individual objects at the same time. While spectroscopic technology isn't new, the ability to see up to 100 objects at the same time is. This is an example of the data it will collect. Each band is an individual shutter's spectroscopy reading. Each shutter is also amazing in that it is only the width of a few human hairs. More bespoke devices that had to be designed specifically for this telescope were the infrared camera sensors. These are state-of-the-art, the biggest and most sensitive infrared detectors to ever be made. There will be 3 different detectors, each for different wavelengths in the infrared. They are very advanced in that they don't just take one sample per pixel, but several, meaning they can reduce noise and sense if a cosmic ray hit the pixel and can cancel it out. Another design issue they had to deal with was excess heat. As I mentioned, infrared telescopes are extremely sensitive to heat, even heat generated by the telescope itself. There is a radiator designed into this side to enable the telescope to radiate any heat it generates itself, as the instruments need to be cold, minus 220 degrees Celsius cold. One of the instruments aboard the James Webb Telescope, MIRI, requires even colder temperatures. It can only operate at 7 Kelvin, or minus 266 degrees Celsius. This means it needs its own cryocooler, which is basically a pipe filled with cold helium that flows by the instrument from a pump at the bottom of the spacecraft. Pumps are an issue though because they vibrate, so a super low vibration pump had to be developed. The biggest heat source in our solar system though is the Sun, and to counteract this, engineers designed the Sun's shield membrane. There are 5 layers in all, each thinner than the width of a human hair, to keep the mirrors cool and protected from solar rays. This membrane means that while the side facing the Sun can almost reach 100 degrees Celsius, the instruments on the other side remain at around minus 220 degrees Celsius. Again, due to launch limitations, the membrane will start out folded away, and when it reaches space it will begin to pull the membrane delicately out over the course of several days until it is fully stretched out. The membrane is in fact one of the reasons for the most recent delay to the telescope. During the testing of this deployment process, one of the membranes tore, meaning they had to replace it and look into the design to make sure this didn't happen in the actual launch. Because this is the big thing with the James Webb Space Telescope. If something goes wrong, there is no way to fix it once it's in space. So they have to ensure that they do everything within their power to get it right the first time. And with such a complicated design, there is so much that could go wrong. Just look at this launch process for it to get to its final orbital location, which by the way is the L2 Lagrange point behind the Earth and beyond the orbit of the Moon. It's crazy. Nothing has been attempted on this scale before, and I don't know anything that will match it for a while to come. The James Webb Space Telescope is actually built now. Everything is completed. They are just thoroughly testing each and every one of their systems to make sure everything goes smoothly come the launch. Because if this mission is a success, just this one telescope will unravel so many of the mysteries of the universe by itself. Hubble was already a wonder, but this will be a serious step up. Well, thanks for watching. Do you enjoy the science